Hi, everyone. Can you all hear me? Okay, great. So we realize that we are the last session, which is keeping you from the happy hours. So we'll try to be quick and not as boring. So so quick introduction for us. Myself and Bo both are SAs with AWS, with the containers org and the open source. So we deal with all the open source and containers things. So today our talk is about how to optimize distributed query engines on Kubernetes. The way that we will go about this is I will give you some basic introductions and the challenges that we see when it comes to deploying like distributed databases on Kubernetes specifically. And what do we see as challenges from the field? And then how we are making use of the observability solutions, things like KEDA and Karpenter, to overcome some of those. Okay, so what are some of the challenges that we see when it comes to big data and GenAI workloads? The first one is obvious, which is massive data processing, right? So we are talking about exabyte scale of data. And since the proliferation of data is growing, so that means the sources of data are also growing. And when it comes to the GenAI pipelines specifically, the models and the data sets that are needed for the training of these models is also growing. So all in all, we are dealing with massive data processing here. And we need some sort of powerful query engines to deal with that kind of data. The next one is also pretty significant, which is like heterogeneous data sources. So now, like if you're talking about different data sources, right? So you have if you're coming from the big data world, you have different disparate data sources. Like you have your IoT sensors. It could be your object storage. It could be even your RDBMS systems. And when you have to query from all these heterogeneous data sources, it obviously presents some challenges. Like how do you actually interface with all of data? And how do you present that data to the callers, right? So that's where the query engines come into the picture. The next one is, in most of these cases, and it depends on the use cases and the applications, but most of the cases you are dealing with very low latency requirements, which means that you have to respond to the queries pretty fast. And the last but not the least in any way is the cost efficiency. Because if you are dealing with that scale of data, then you need an infrastructure and a mechanism to keep your costs down. Otherwise, it could go out of control pretty quickly, right? So all of that brings me to this one, which is kind of shows the different data access layers. So at the top of the chain sits the BI tools. So think about your Tableau, Power BI, or even your custom applications, or let's say QuickSight dashboards, right? So that is your caller that is accessing the data from the query engines. So on the query processing layer, we have some examples here, things like Trino, Presto, which is the predecessor of Trino. Then if you're dealing with Apache Spark, it also has the SQL capabilities. And then if you're dealing with like managed services, then Amazon Athena would be one example. And there are many more tools other than this, but this is the layer where the processing actually happens. So how does the query processing layer actually does its job, right? So underneath, there is a cataloging layer that takes place. So anyone familiar with any cataloging system like Hive, Glue? Okay. So basically, the job of the cataloging layer is to, as the name suggests, catalog the data. Because when you are dealing with this massive scale of data, you need a solution like Hive or Glue to actually properly catalog your data. Means some of the data governance aspects, things like data quality, the contextual data, so that you are dealing with the right sort of data for your applications. You're not dealing with garbage data. So all of that is taken care of at the catalog level. And then comes the storage layer, which actually physically stores the data. So it could be your object storage, your cloud storage like S3 or GCS, your table formats like Iceberg, which is very popular, like open table format. We have also Hoodie catalogs. Then if you're coming from the Hadoop world, then HDFS is a pretty well-known mechanism to do it. And even your RDMS systems like PostgreSQL or MySQL DBs, right? So this is kind of the data access layer and the flow of data that happens. So how does the query engines actually solve the problem that we laid out in the first few slides, right? So first thing is that query engines, and we are going to focus on a Trino on a little bit here because the scaling mechanisms that we are going to talk about focuses mainly on Trino, but most of these principles will apply to any query engines. Like think about Dremio or even the upcoming ones. Anyone using like things like DuckDB here? Have you heard of DuckDB? So there are a lot of emerging tools that are coming up in this space, but our talk will primarily focus on Trino. So what Trino does is, it will query these disparate, diverse data lakes. And data lake is another different topic. It could be very complex in its implementation, but we are just showing a simplified version of it. So basically what Trino does is it will query all those data sources and then sends back the result to the downstream apps. It could be your business intelligence apps, interactive query engines, or your even analytics apps. So the main key takeaways from here is that it can deal with, it is designed for high scale, which means that it has like massive parallel computing infrastructure built into it. For instance, Trino is basically written in Java, so it makes use of Java multi-threading and tries to give you that performance. Then, like SQL analytics, it's basically an SQL engine. So if you're familiar with SQL, but you are dealing with these disparate data sources, it gives you a pretty unified interface where you can just work with SQL queries. And it makes use of federation. So data federation is one of the key components of any query processing engines. And the other important aspect is it can query the data where it lives, which means that if you are storing your data, let's say in public cloud storages, right? So Trino can actually connect to that data source with connectors. It has a lot of support for different connectors. Then you don't have to move the data. You don't have to migrate the data, or you don't have to transform the data, because that involves a lot of cost and migration effort. So what these query engines can do is query the data where it lives, which means that you are significantly reducing your cost and effort. These are some of the tenets of the query engines. Now, first one is separation of storage and compute, which means that it enables you to independently scale your storage and compute. So those are decoupled. You no longer have to combine the storage and compute when you are scaling your query engines. Then is the coordinator or worker architecture. This is also Trino specific, but other query engines also implement similar kind of architecture. So coordinator is like the brain of the Trino cluster. It basically coordinates with other workers, so that's why the name. And the workers are like minions in Kubernetes, so that actually deals with your query processing. So it is actually the workhorses. The third one is data locality optimization, which is it can query the data close to the source so that you don't have to migrate it to minimize the movement of data. And think about it, in a cloud environment, let's say if you're migrating data, it can incur significant cost, right? So that's a big feature of query engines. And last but not the least is fault tolerance. So we'll go into the architecture and we'll see how the fault tolerance is inbuilt into these architectures. It can recover pretty quickly from the worker node failures. So now we have given the introduction of how all of this come together. So the question is, why would you use Kubernetes for this, right? So what we have seen over the last couple of years is there is a shift towards migrating this data and ML workloads both on Kubernetes. And Kubernetes by now has become so mature that our platform team's de facto choice is Kubernetes. So it will give you the scalability of the compute layer, the orchestration, because Nowadays, pretty much all the workloads are containerized, so you get that massive orchestration layer benefits. And then portability is also obvious. But apart, like with all of this, I think the standardization is probably the most compelling reason, because as I said, like most platform engineering teams are so comfortable with Kubernetes now that they are kind of like the data science team, the ML team, the data engineering team, all are coming to them to deploy their workloads on Kubernetes, because there is just so many standards that are implemented in the Kubernetes layer, right? So that is one of the big reasons that we see this momentum shift happening. Okay, so let's dive a little bit into the deployment architecture on Kubernetes. And again, this is specific to Trino, but you can find similar architectures for other query engines as well. So what happens is, for Trino specifically, when you submit a query, and this is a CLI, the Trino CLI, if you have used Trino, you must have used it. So basically, when you submit a query, then it goes through the coordinator and the worker nodes. So in a Kubernetes world, the coordinator and the worker, they are represented at pods. So the coordinator, as I said before, is the brain of the Trino cluster. So basically, it receives the query, and there is a lot of phases that it goes through. So there is a component called parser, which basically parses the query. Then it goes through different stages of planning. Like it plans the query, depending on the complexity of the query that you are submitting. It will go through multiple stages. And finally, it will come to the scheduler component of the coordinator. And the scheduler will decide how many worker nodes or worker pods are needed to basically handle that query. And it all depends on the scale. So the good thing about Trino specifically is that based on the scale of your query and the size of the data set that you're dealing with, it will dynamically scale the worker nodes. And I think we have like some talks about Karpenter here. So Bo will go into the details of it. But basically, the advantage of using Karpenter here is that you are using just-in-time nodes, right? So you're not wasting your resources. So as soon as Karpenter will see that there are pending pods for the coordinator and the worker, it will start provisioning new instances for you. So then when the query comes to the coordinator service, which is a Kubernetes service, it goes to the coordinator, and finally the scheduler will try to spin up worker pods. Then let's say you are dealing with, let's say 10 data sources behind the scenes. So how does it work? So the workers in turn will make use of those different connectors that Trino provides to connect to those underlying data sources, then get the data, aggregate the data from those queries, and then send it back to the coordinator. And all of this happens very fast, and it's like a buffered output that the coordinator sends it back to the Trino CLI. And you don't have to use Trino CLI, but it's a very handy way of testing your queries. You can connect with HTTP, direct HTTP endpoint as well. So when it comes to the scaling part, you see that we are using KEDA, Prometheus, and Grafana. So KEDA, we are using for event-driven auto-scaling, because if you are dealing with just CPU and memory-based scaling, it doesn't work well in these specific scenarios, because so in the auto-scaling world, we say that you choose a metric to scale on which is directly proportional to your load. Otherwise, you will not get the benefit of auto-scaling, right? So that's where KEDA comes into the picture, and we have an example showing that how exactly we can do it with Trino here. And then we are using Prometheus to export the metrics, and you can also visualize those in Grafana dashboards. So that's how the entire architecture works. So with that, I will hand over to Bo for the next section.
Well, let's talk about observability first, right? So we know Trino is a distributed engine, it's a distributed system. With distributed system, observability is always a challenge, right? Because it's hard to monitor the overall system behavior. It's even harder to troubleshoot the issues or performance problems, because it could happen anywhere in the system, right? It can happen on any node, and sometimes across multiple nodes of the distributed system. That's why we like Kubernetes to be the platform running Trino and this kind of distributed engines, because it allows this decentralized observability approach, right? It allows you to every single part, coordinator, worker, to expose the metrics and the logs locally, right? Then it can depend on our service at the cluster level to collect, aggregate, and eventually analyze and visualize them centrally. We choose to use the Prometheus in this case to collect metrics. We use the OpenTelemetry collector to pass through the trace, and we use a Fluentbit to aggregate all the logs. We're by no means saying they're the only option or the best option, right? They work well with the Trino on our blueprint, but you are definitely free to choose whatever observability stack that fit your overall observability requirements. The key is no matter which one you choose, right? It should be independent. It should be loosely coupled with your workload. Meaning, when you switch from Prometheus to say OpenSearch, you shouldn't have to require Trino, any change on the Trino side. From Trino, focusing on the metrics at this point, right? There are many ways of exposing metrics from Trino, including our monitoring endpoint and on its own coordinator, right? But in this case, we choose to enable GMX. Trino supports GMX. With GMX, it supports a wide range of metrics through the GMX interface. That GMX interface is independent to what we choose on the observability. Since we are using Prometheus, we also need to use a GMX exporter that basically retrieve all the metrics, all the objects from GMX interface, then export them on our Prometheus compatible endpoint. Right? That's the purpose of GMX exporter. With the Kubernetes, again, another benefit of using Kubernetes in this case, it allows you to use this sidecar pattern, deploy the GMX exporter to extend the functionality, the observability functionality of the core Trino coordinator or worker path, right? So you don't have to make any change to the main container, and it automatically gets the capability to communicate with the Prometheus. So go to the next slide, right? Here's a quick example of the GMX exporter. You can easily enable GMX and set up GMX exporter through the Trino Helm chart. I don't expect people to read the whole manifest, right? What's important on this one is one, you set up the host port to point to the registry port of the Trino GMX. And you also need to set up a whitelist or include a list of objects because Trino exposes a whole lot of objects, and we want Prometheus to scrap those objects, serve the metrics in a very short scrap interval. So we want to filter that at the GMX exporter level, and we don't want to overload the GMX exporter. Right? Once we decide what to export on the exporter, Prometheus will do its job. It will scrap all the, discover all the paths. It will scrap all the metrics from those paths. And eventually, we will use the Grafana to build that one dashboard to monitor everything, right? To display, visualize the metrics from the worker, from the coordinator, from the Kubernetes infrastructure itself, all on the same dashboard, have that single pane of glass view. So that's the observability part. I mentioned, right, so we use a very short scrap interval, and the reason of doing that is really to support the auto-scaling. One of the benefits of the distributed system is the scalability, right? We implement all those tenants, right? We separate the coordinator and the worker. We make the worker stateless, so it can be scaled horizontally, right? And Kubernetes support that also, right? Because Kubernetes allow you to easily, quickly scale in and out your workload by just increasing or decreasing the number of replicas in your replica site. But there's still one question remaining, right? It's a when to scale, right? Kubernetes comes with HPA. We have talked about HPA. We have talked about the horizontal part autoscaler. It works well, but the problem with HPA is that it depends on the consumption metrics, the CPU and the memory utilization from the metric server. For I wouldn't say any, for most distributed systems, that consumption-based metrics don't work really well, right? The reason for that is when we design distributed systems, right, we want that system to be stable, regardless of what the load is, right? So we're not just sending all the requests, all the queries down to the workers and overload them. We implement all kinds of mechanisms that can be throttling, queuing mechanism in between asynchronous communication, just so whenever we have a load that's going to be heavier than what a current worker can handle, we queue them up. So if our HPA is dependent on the CPU and the memory metrics or utilization, it may never, the scale may never happen just because the workers are not under stress while all the users are seeing degraded performance, right? So in that case, that's why we, for the auto scaling of this kind of distributed system like a Trino or Kafka on Kubernetes, right? We design, that's why we have this KEDA solution, right? The Kubernetes event-driven auto scaling. The selling point of KEDA is in the name, right? So it can scale the system based on the event, like a request received, a query received, not solely based on the consumption utilization metrics. For Trino specific, right, it exposed from the exporter, right? We scrap the metrics like a queued query length, number of required workers, and we can use this one to determine whether the system is under heavy load, and then KEDA will kick in to scale out the worker deployment. Another benefit, I think I mentioned in previous sessions as well, KEDA support the scale in and from to and from 0, right? Using the number of required workers doing deactivation and activation. That allows us to optimize and minimize the cost of the Trino cluster, especially in a non-prod environment. KEDA works off this CRD called scale object, very self-explanatory. Couple things we pay attention to is really to set up the target, the triggers, right? We use the Prometheus triggers. KEDA support tons of scalars, tons of event sources. In this case, we use Prometheus as the event source, as the trigger. You can use your Proms QL. You can set up the scaling modifier to combine multiple metrics together to decide when to activate the scaling and when to scale out the workers. There are other parameters like a pooling interval, cooldown period, just to control the speed of scaling. Next one. So that is the scaling for the worker part and worker deployment, right? We think we want you to use Kubernetes to enjoy the dynamic resource management for cost efficiency. I think previously mentioned, right, in the cloud environment, we can use the cluster autoscaler and the Karpenter to scale the cluster, right, based on the demand from the Trino cluster, right? Karpenter is the AWS response to the cluster autoscaling in a cloud environment. We see there's a lot of benefit using Karpenter, over the traditional legacy cluster autoscaler for a Trino cluster, right? For one, it's the speed. Karpenter can support this rapid provisioning we talked about, right? It can react much faster, and it can determine what to scale and when to scale. It doesn't really go through another layer of component like an auto-scaling group or scheduler itself. It basically can provision the EC2 instances or any other cloud instances directly through the API, and also schedule the part onto those new nodes directly as well. Karpenter is also much smarter, right, in this case, because we launch the workers and coordinators maybe in different sizes, and with all the other workload, Karpenter, unlike the cluster autoscaler which can only scale out when there's a pending part, right? Karpenter will consolidate, will consider all the requirements, and then basically decide what the instance size and what is type to use, whatever is allowed. It's also a lot more flexible, right? With Trino, right? We separate the coordinator and the worker, and we decided to use different node pools for both. Right? With the workers, we also want the Karpenter to pick the most cost-efficient instance for us. That's not only the efficient instance size and type, that's also including a support for spot. So for workers, we like Karpenter to choose spot instances when it's available, when it has a good spot price. Let's go to the next one. So here's a very quick example of the two node pools I use for Karpenter. For Karpenter, I use for Trino. I was gonna let people play a game of spotting the difference, but we don't have time. So I'm gonna just point out, right? For the coordinator, we want that to be stable. We don't want that to be disrupted. So in this case, we can set up a Karpenter to use on-demand instance only, and also only consolidate when it's empty. On the other side, for the workers, we do like to scale faster, and we also like to be cost efficient. In this case, in the node pool, we can specify to use a spot instance, right? Somewhere in the middle, you will see the instance the capacity tab, we have a spot in there for the worker node pool, and also we allow that to be routed. We like to consolidate all the nodes when it's underutilized. Like I said, the node pool definition, the manifest will show all the flexibility Karpenter has, right? You can specify different sizes, different type of instance to be used in each of the node pool. Right.
So just wrapping it up, like we have this project, you can scan the QR code. So this is a project that is open source, and we from AWS and some of our community members, including our customers, they all contribute to this project. So this is a place where we have Terraform-based templates for deploying this kind of data engineering architectures and also ML architectures on EKS specifically. So feel free to check this out. With that, I think we are right on time. Any questions?